So Mark is, I guess I've known Mark for quite some time now, actually. I think since I first came to the Netherlands. He did his PhD at Utrecht in a group of Daniel van Magenberg. Many of you probably know him. He's famous for quantum dots. And Mark had some of the most beautiful pictures I've ever seen on nanoscience, these amazing assemblies of quantum dot lattices and superlattices. Just amazing TEM images and a really beautiful science there. And then he decided to switch into NWO. So he became a program officer at NWO and helped support lots of different programs, was also one of the liaisons for the NWO-I Institute, so also got to know him there, and then decided to switch again and go into managing the IRIS Institute, so the Eindhoven Institute for Renewable Energy Systems, is that right? Yeah, and has also been the secretary for NERA, the Netherlands Energy Research Alliance, and so has been really an important player in the Dutch landscape in terms of sustainability and energy transition for a decade now, I would say, yeah. And so it's really an honor to have him here and to discuss his views on the energy transition and a sustainable future. So please, Mark.
Okay, so thank you, Erik, for this very nice introduction. I feel very honored. Yeah, so despite me being from a technical university, I was asked to give a little bit broader overview of the energy transition, where do we stand? And I was challenged by colleagues within my university to also put the societal perspective in there a little bit more. This happened due to a glitch in the program where my talk was first announced with the title of the speaker from previous year, which was Helene de Koning. So Helene said, "Oh, you're going to give a talk with exactly the same title as I did last year." I said, "I'm sorry, that's not going to happen. This is the talk I'm going to give." And then she said, "Oh, but this is all technical stuff. Can you not include the human perspective more?" So I tried to do so, and she may judge later if I succeeded. So what I will be talking about is modular scaling to speed up the energy transition. And in order to do so, I would like to first point out where do we stand currently in the energy transition? What do we see as possible pathways for acceleration? And how can manufacturing industry help in doing that? And then there is the more human perspective, because I see something interesting happening at the moment with consumer dynamics actually determining some aspects of the energy transition. And I think PV is a perfect example where you can see this happen, so I will illustrate that. Then some considerations on that and some conclusions, and then I'm very happy to take all your questions on this. So, where do we stand in the energy transition at the moment? If I give talks like this, I always start with this graph, because this graph shows in the past 2 decades and a little bit more, the global energy consumption, worldwide energy consumption. And what you immediately see is that it is still mainly built up out of coal, oil, and natural gas. And this is, of course, the problem that we have, because the challenge that we face is that within a similar time frame that we have here, we have to flip this graph. And this green share here, that is under 10%, that is the penetration of renewables in the global energy consumption, needs to be this share. That's what we have to do in the similar time frame as we see here. So that's a huge challenge, I would say, and that's what we are all working on. Maybe to drive home the point about what kind of volumes we are talking about, I did some back of the envelope calculations and tried to visualize what kind of volumes of energy carriers we're talking about. So the annual consumption of oil equals oil trucks filled with oil lined up around the circumference of the Earth 50 times around. Every year that's what we consume. Gas, Hindenburgs, by the way, the Hindenburg was bigger than the White House, filled with natural gas, lined up around the circumference of the Earth 125 times. And a train filled with coal, hoppers filled with coal, 24 times around the globe. That's what we use each year. These are the volumes that we need to change. So that's a huge challenge. Maybe to bring it home even a bit more for you personally, the average person here in the Netherlands consumes on a daily basis 1.25 kilograms of coal, 4.5 liters of oil, and 5.5 cubic meters of natural gas. And that's excluding the international transport by shipping and air freight. So that's the challenge. Maybe to To then structure it again a little bit, if we look in the Netherlands, a typical developed economy, how do we use this energy, where does it come from, and what do we use it for? There is each year this very nice overview from ABN, Energiebeheer Nederland, with an infographic that I highly recommend to read, because it's very informative and illustrative of where we stand in the Netherlands. And I think that is illustrative for most of the developed countries that are currently facing this transition. So what do we import? Mainly gas. We are still very gas dependent. We have, of course, a rich history in gas. Oil, not so much coal. Other countries have more coal. And we use that then for several sectors that I will point out. I think the important thing to point out here is that already in this transition from what we import and what we use, we lose 24% of our energy. 24% of the energy is lost in the system itself. And this is mainly conversion losses. And that's mainly the conversion losses when you convert actually fossil energy carriers into electricity. So in that sense, do not underestimate the penetration of renewables that are already directly electricity based, because that will help solve this problem. But there's also distribution losses. Of course, electricity has that problem as well. And usage within the energy system itself. So then in a typical developed economy, this is used roughly one third for the built environment, the industry, and transport. And in the Netherlands, it's skewed a little bit. We are quite industry heavy, which also at the moment that you then look at what kind of modalities of energy carriers we use or what we use it for, then you will see that there's quite a large share of heat, which is also a lot of high temperature heat in the industry, but also industrial feedstock. So these are the typical numbers that describe where we stand in the Netherlands. And of course, we know what this leads to. This is what we have seen. This leads to the emission of greenhouse gas, of CO2. And if you see this CO2 emissions still rising, people say, okay, but what about the COVID crisis? What about the economic crisis? Is that not going to change? They hardly have any effect. So what we see here is that we really need a system transformation. Incidental actions will not solve our problem. You will see an effect. I mean, especially the collapse of the USSR has quite an interesting effect on emissions, but then you usually see that afterwards it's restored by another economic boom. And I think after COVID we are experiencing that at the moment as well. I think as the Netherlands, we should maybe be a bit more concerned than other countries about this fact. This is the Netherlands as you usually do not see it. The north is to this side, but this is to illustrate that the Netherlands is actually really a delta area. We say this, but here you see it. We are a delta area of large rivers flowing out of mainland Europe towards the sea. So this means that we are prone to flooding from seaside, but as well from the riverside, as we have seen, for example, 3 years ago in Belgium and Germany, and we have seen this week again in Bavaria. So a quarter of our land area is below sea level. Half of our land area is not elevated more than 1 meter above sea level. So I think we have a challenge there. At the same time, we are ideally located to take a role in the energy transition to speed things up. We have here the harbor of Rotterdam. That is the main gateway to the large industrial sites in Europe. What many people do not realize is that if you take the chemical industry in the Netherlands, especially in the south of the Netherlands, together with that of Flanders and that of of Germany, and you make a triangle and you add that up, you have the third chemical cluster of the world. It's really huge what we're doing here. Some of them are shut down now, but still we have a large history of chemical industry here. And if we can transform that, we can also accelerate. And then, of course, we have here in the north, we have the natural gas infrastructure. And with the push to hydrogen, I think we can also take an interesting role there to accelerate the deployment. And there's many countries worldwide looking at the Netherlands at the moment for the role that they take with respect to hydrogen. So lots of comments to be made on this. I'll not go into that, but I think we can take a leading role. We have assets, we have the knowledge, we have the infrastructure, and I think we should do so. So maybe to illustrate again the current importance of this. This was just this week. This was last Monday. The news, the floodings in Bavaria. 6 people are killed at the moment. this is happening now, this is happening here, and it's up to us to do something with it. Then next to global warming, there's of course another aspect to this energy transition that we have to face, and that is the global tensions that are increasing, and the role that energy plays in this. 2 years ago, we have of course seen with the gas crisis in 22-23, with the terrible invasion of Ukraine by Russia, we have seen how dependent we have become as Netherlands, but also as Europe in general, on energy import, and how dependent we made ourselves of a single supplier and a single source. And this has driven the prices to extremities that many people here have experienced at that time. And I think we were saved in the end by the much condemned fracking shale gas from the US, which of course is not something that we wanted. But it shows to me that we need to diversify in sources and in suppliers of energy, because I think it's an illusion that Europe will become autarkic, self-sufficient in a short term. At the same time, we need to consider about every measure that we can take now already, and that's what this ABN graph also shows, both on the import side, but also to raise our own energy production, and maybe even go so far as to consider the decline in fossil carriers, to maybe take some steps there to do that less fast. It's of course something for the climate change you do not want, but for this respect, this is something to consider. So that's sort of the stage where we are now, and at the same time we see this interesting dynamics already happening of the energy transition that are just going already and crossing through this discussion. And then of course this is something I don't have to explain here, but for me it's good to tell it every time that I tell this story, to highlight again what the problem is of renewables. The problem of renewables is that we have a dislocation in time and space between the production and the usage. So we produce energy where we do not use it, or we can produce more energy where we do not use it so much. And in time, we usually produce it more when we do not use it so much. So that means that we need devices that can store energy. We need devices that can transport energy. So the transport, the conversion and the storage of energy, that's for me the key challenge at the moment in the energy transition, and that's what we should be working on. At the same time, of course, also the upscaling of all the production. But I think in the lower TRL levels, this is the bigger challenge at the moment that we have to face. And then, of course, even though the penetration of the renewables in the total energy consumption is below 10% globally, and for the Netherlands it's a bit better, it's about 15%. In the electricity grid, by times, it's of course more than 100%. So at the same time that we are electrifying our supply, we're also electrifying our demand, and this has led in a very short time frame to a complete deadlock of the electricity system in the Netherlands. I think we have seen good measures that really helped in deployment of PV, which was great, and of wind. And now we see that we have been lagging on the infrastructure side. So to me, this shows these are some of the struggles at the beginning of a transition, of course, that we have to face. But it also shows, and that's a conversion point, it also shows that electric only for the short term is not a solution. I think ultimately we will go to electric only, but at the moment we need to do useful stuff with electricity also at the moment, that we cannot feed it into the grid. So what's then the bigger picture? Maybe again to drive it home, we need devices that are able to convert energy into different forms, different energy carriers. So this is a very nice picture of the European Commission System Integration Working Group that actually shows in one picture the transition that we are going through. We have currently these parallel systems for different energy carriers, for oil, coal, gas, and electricity, that are very much top-down organized, often very wasteful along the chain from the beginning until the end user. And where we are going is this highly integrated energy system where different energy carriers need to be converted into each other with a high frequency from A to B and from B to A at another point in time, and with high efficiency, low losses. And the losses that we do have, preferably use that as heat in a useful way again. So again, we need devices that can actually do this. We need to build stuff like batteries, electrolyzers, etc., heat pumps. And at the same time, we need to organize our energy system much better to actually facilitate this. And the System Integration Working Group of the Top Sector Energie, so that's the Netherlands one, has actually a very nice model laid out. They call it a holarchy, a holarchic layout of the energy system, where a holarchy is a sort of the intermediate between a top-down led hierarchical system and bottom-up, well, chaotic system, heterarchy, but it's just chaos. So it's sort of the in-between where you have a loosely coupled system of systems where, and it sounds so simple, where on the most local scale you try to optimally balance the production and the usage of energy. And you would say, this is so simple. Why are we not doing this like this already? Well, we're not, because at the moment the infrastructure is not organized like this. It's still organized with some remarks as a copper plate where you can just prick in your supply and take out your demand. And it just doesn't hold anymore. So this is a movement that we're making. And this then also leads to interesting, and then we come to the consumer dynamics, to interesting dynamics in the kind of equipment, the kind of devices that you can actually use in that system. So let's have a look at that. Because the question, of course, that we face is how fast will this energy transition go? I've shown this graph, and then in Paint I just draw some lines to see, to give an idea how fast will it go. Adoption of technology typically goes in these like S-shaped like curves, where you have exponential acceleration at some point, and then you reach a plateau. So the question is, how fast can we make this happen, and how high can we raise the plateau? And these kind of dynamics, they usually depend on the way that a certain technology is adopted. And in that respect, if we look at PV, we see some very interesting dynamics. So if we look at the way that PV has been adopted versus the way that people predicted that PV would be adopted, we see a large mismatch. And my colleague Auke Hoekstra has had some very nice Twitter feed about this, or X feed I should call it now. And he just plotted all the predictions of how PV would be rolled out in the World Energy Outlook. It's the International Energy Agency. This is like the Bible of the energy transition. And he showed that each time they heavily underestimated. Yeah, well, the Bible was wrong, clearly. Huh? That's the point. That's the point. Okay, but fair enough. But IRENA, which is the International Renewable Energy Agency, made the same underestimations. Even Greenpeace, who had the most optimistic scenarios, also severely underestimated the rollout of PV. So fair enough. With this one, it's maybe the nicest to illustrate, but the other ones also underestimated this. And then the trick that he played, and that actually really nicely showed what was wrong with the models, was that he just, instead of putting all the predictions out there and adding them together, he just showed what would then be the additional deployment of PV, assuming this line. And then you see that you just have like status quo. They would just update their numbers of how much PV was actually out there and run the same model that gave the same result, which was basically hardly any growth. And that's what you see here. So the modeling of these kind of developments is completely wrong. And where does that come from? In my mind, this comes from the fact that energy, the way that we used energy in the past was very heavily dependent on the way that state-led companies actually, with the dynamics, the mechanisms behind that were led to make investments and to actually extract energy, and you have a very interesting market mechanism behind that. But here we see something different. We see that there is a different mechanism going on, and some call it tipping points, social tipping points. I think for me it shows, on the one hand, that the way we model this is not good anymore, and I will go into that in a bit more depth in 2 slides. But also that there's another type of dynamic. So it's really different from the way that we used to do things. In climate change, we of course see similar effects. We also see tipping points, and this is what most people know it of. And I think for all the chemists, it's just a chemical reaction from a state A to B, where you have a threshold and you need a catalyst to go through it. So for climate change, please don't do it. But for social change, this would be something good to go from state A to state B. And if you do this in modeling of social dynamics, you see that people call about laggers and early adopters, etc. You get this mechanism where people, at the moment that there's one house in the street that have some PV and the neighbors ask, and then suddenly in a short time frame, the entire street has it. This is a very different kind of mechanics, of social mechanics, and it is a change from having energy carriers as a commodity towards energy systems as a commodity. So rather than the oil, the gas, and the coal being the commodity, the PV panel becomes the commodity. And suddenly the customer dynamics that are happening, that's us, and we talk to each other, and you get a very different kind of adoption mechanism, and we see that for solar, we see it for batteries, for electric vehicles. I'll go into that in more detail. So that's an interesting dynamic to go through. And it's also related to something else, and that is the way that our old energy system used to be organized mainly in very big assets. So we have here a coal-fired power plant or a hydropower dam or a steam methane reformator, that is where you make hydrogen out of natural gas. These are big chemical plants or big facilities that usually have a tendency to be over time and over budget when they are realized. And we now see that the stuff that's penetrating, the renewables that are penetrating in the energy system are a very different kind, more modular organized or granular organized systems. So like the PV panels or the battery energy storage or the containerized electrolyzers. And this paper from 2020 in Science shows very nicely, looking back at the deployment of different energy technologies, that more modular organized energy technologies know much faster market penetration, much steeper learning curves, so they diffuse much faster into the energy system than the bigger stuff. Also, they tend to be more efficient, and since they have a shorter lifetime and they are less complex, there's less risk of a lock-in, of a technology lock-in. And I think in this stage of the energy transition, that's crucial. We're currently having this discussion about nuclear. Don't take me wrong, I'm not against nuclear per se as a technology, but if we would at the moment buy 3 more nuclear power plants in the Netherlands, you can just extrapolate what the kilowatt-hour price will be of that electricity, which we will have to pay for the next 4, 5, 6, 7 decades. And we will not be competitive with PV or wind in Spain. Also, this kind of technology tends to be broader accessible. I always visualize that if you roll out PV in Africa on a household scale, this is accessible for everyone if you can buy a small panel or a bit larger panel and maybe some battery storage. Whereas such a hydropower dam usually goes associated with a chemical company that's sitting next to it, using all the energy to make their goods. And then the societal benefit is very limited to a small group in society. So these are very nice things to take into consideration at the moment that you make technology choices, and if you think about the fact that we have 20, 25 years left to make this transition happen, what kind of technology choices you make. And this is the point I drive home in the Eindhoven region, this way of thinking about modular scaling is how our manufacturing industry actually thinks. This is what they do for ASML, this is the consumer electronics for Philips. Why not make energy systems? That's what I then say to VDL and to et cetera, et cetera. Yeah. So in a more popular way, reading about this, this is a very interesting summer read. So I don't have any royalties or whatever, I'm not involved, but for your summer reading list, I would recommend reading that book. Now going back to PV, this is the graph of Auke, and he recently updated it. So the trend still holds. The trend still holds. Is it only for PV? No, like I said, we see this for more of these granular or modular energy technologies. We see these very rapid penetration curves or learning curves, and we see that for wind, for solar PV, for batteries, for power to X, so that's the electrolyzers there. Also very interesting to look at actually at the dynamics of nuclear fission. So that also had a very steep learning curve and then very quick saturation. There's actually a paper from Nick Lopez Cardozo just this year that really goes into depth about why that is the case and the way that industry needs to scale with also the deployment of a technology and how that was actually the limiting factor here. I highly recommend reading that because that's one of the best arguments at the moment against nuclear building new nuclear stuff. At the moment that you have it, please don't shut it off, Germany. But that's another story. You see that these learning curves also associated with a more rapid deployment that goes with a decrease in cost, and we already reached cost parity. I mean, I don't have to explain that to the PV community, but for electricity, we already reached cost parity on many things, and I think for electrolyzers in a couple of, hopefully years, but maybe in a decade or so, we will also reach that. And with batteries, etc., we are already there. We are now fighting against the rest of the system. So, if these are the dynamics that we are taking into account in the deployment of the new energy system, there's some other stuff that we need to think about. How are we going to do this without creating new problems? Because deployment of a new technology and these consumer dynamics, it goes associated with buying a lot of stuff that has a short lifetime, and then at the end of the life, it also goes somewhere. So changing from energy as a commodity to energy devices as a commodity, if we do not do that in the right way, it risks changing from the problem of greenhouse, from our Earth turning into a greenhouse, from turning our Earth into a scrap heap. We really need to think about the materials that we use, about design to recycle, about the way that we do the end-of-life use. And you can see that at the moment that you see here in the application of kind of raw materials, the traditional fossil energy carriers, they had a much less demand on both the volume of materials, but also the diversity of materials and the geopolitical consequences associated with them, which is what we see here. So we make ourselves very dependent on other countries. I was very happy to read yesterday or the day before that in Norway there was a huge deposit of rare earth minerals actually discovered. So that was hopeful. But still, we need to really think about that. And it's not only the rare earth metals or the metals themselves, but it's also about the production technologies. So the energy intensity of producing silicon, purified silicon, but also the PFAS stuff that we make and the way we handle that. So these are things that we really need to take into account, and also in the design choices we make for this kind of more consumer-led technology. Because at the other end of the line, there's someone like this that has to go into a hole in the ground to actually bring those materials up. So for PV, because PV conference, so I thought to calculating the ambitions that you have set down in the Solar NL program, again, some back of the envelope calculations, and I already discussed this with Albrecht, he knows. I was calculating, this means that you need to produce 1 square meter of PV panel for just the Netherlands per second, 24/7. From now until you manage to realize this 1,250 square kilometer. So that's for the next 28 years. And then if you think about the lifetime of the panels, we will keep on producing this and probably even up the production rate a little bit. So for the industry, this is really good because it will prevent the same thing that happened to nuclear. It will prevent that the industry actually dies and then at the end of life has to really start up again. So for industry, this is good. But again, the material usage, you really have to think about what kind of design choices do you make, especially now with perovskites, with multi-layer solar cells. How are we going to delaminate the stuff? How are we going to get back the materials that we've put in there? And then preferably also in an not too energy intensive way. So then some end of the talk conclusions. Will it be fast enough? Actually, this was an idea that Albert Polman gave me in a recent talk of his. And he highlighted the report of the doomsday clock. I don't know if you know the Bulletin of the Atomic Scientist. This is what was published shortly after they dropped the bomb. And they basically, based on a number of indicators, give sort of an indicator of how close are we to the end of the world. It's not a nice topic, but and you see that it relaxed at the end of the Cold War, and now we're back up there again. But actually, if you look into the report of this year's Bulletin of the Atomic Scientist, it's very nicely to see that despite the increased geopolitical tensions, despite the risks that they see in AI and in nanotechnology and other technology developments, they gave a mixed outlook for climate action. So it's not hopeful yet, but there is some shimmers of hope in there. And that's actually this rapid deployment of renewable energy technology that they give as an indicator and that they use as an argument for having this clock being set at 90 seconds to midnight, keeping it at 90 seconds to midnight and not changing it to 60 seconds at midnight. So that leads me to the end of the talk. Some conclusions. I hope to have shown you that the energy transition requires a rapid acceleration and a radical system change. And in my mind, that the key challenge that we need to work on now is the transport, the conversion, and the storage of energy and the devices behind that, and the upscaling of that. And that this asks for a redesign of our current energy system and the way we interact with it. And that this modular scaling and a holarchic layout of the energy system actually provide acceleration pathways to do so. And if we can do this fast enough, and if we can do this in a fair way, and make a better world out of it, that will depend on the actions of our generation. So, thank you for your attention.
Great. Thanks, Mark, for a really nice talk and a great introduction to the symposium for this year. So who would like to start with questions for Mark? Bruno.
I can start. I have a question on your slide 28, which is also on the Renewable Energy Agency, the International Energy Agency, the material use. Of course, I really agree that we have to make all the renewable technologies from recyclable materials and design them for recycling and so on. But also from your colleague Akke Hoekstra, he always mentions when he sees this graph that they exclude the fuel use. So whatever you already do now with current technology, you're already replacing so much fuel use, which you can never recycle, right? You just blow it in the air. That is already better to do it. Of course, in the future we have to do it even better, but this graph, I think, because it ignores fuel use, is a bit deceiving.
You're right there. So the CO2 is not in this graph. So if you're talking about materials, the carbon dioxide emissions is not in this graph. Is that what you mean, or you mean also
or just the coal and the oil and the gas, which is also a raw material, which is completely ignored here.
Fair enough.
Which
you're right. So that is true, but it does also highlight that other materials will be needed and other dependencies will. But I agree with the point totally. Yeah.
So thank you, Mark. Not a critical question, just a suggestion. I like your visualization of the beginning, where you have 50 times around the Earth, oil transport and so on. So later on, you said that the challenge of the energy transition is to include storage and transport. So that also happened, 100 years ago. So why can you add a visualization of transmission capacity around the Earth, things like that, or storage? I'm just curious.
Yeah, so this is a good point. The challenge to visualize that I will pick up. Thanks. But what we have seen, and we've seen that, for example, here in the Netherlands at the moment, that we discovered the amount of gas that we had in the north of the Netherlands. Suddenly, a country that's relatively poor becomes relatively rich. So the push to actually make this, to build up this infrastructure is huge, and the capital that's available to do so also is suddenly huge. And here we have to fight a little bit an uphill battle. Do you know how long they took to roll out the natural gas grid in the Netherlands? I mean, 6 years. 6 years. They did it in 6 years. The entire natural gas infrastructure that we have in the Netherlands. We will not do so for electricity, I'm sorry. I would like to see it happen, but why not? But because of the sheer amount of capital and political will and force that's behind it. That's my concern. I mean, we saw that this needed to happen for electricity. Everyone has said so already. The grid operators know this for 2 decades. And why is it not happening? Because there is not a huge bag of money and a huge push, because there would be an immediate earning capacity at the rear end by doing so. So I'm not saying that this is a good thing, but this is what I observe is the reason why it's not happening at the moment.
This is why we need a huge PV industry in the Netherlands, because then there is a huge push in the national interest. Other questions for Mark? Yes, Augustine first.
Thank you for the very nice talk. I have a question about the growing in PV and wind that you show that is faster than any prediction. My question is that you mentioned that could be related with social behavior. But do you think that that could have an effect also related with political decisions? That
Yes. I think that if you look at the old mechanics in the energy system, they were very dependent on these political measures around, well, the whole OPEC countries, the way that we dealt with fossils. We have seen that we have had 2 energy crises here, also in the Netherlands, that have given a boost to innovation for renewables as well. And now we see something similar. Like I said, in the deployment of PV in the Netherlands has gone really, really fast. This was also led by a political act, a political measure, which is the salderingsregeling, that is now rightfully under debate. But it has led to a large deployment. So yeah, in the end, political actions will give a push to a certain technology development. But it's then the fact that the old system was, I think, mainly political dependent and has less individual consumer dynamics. And now we see this change to more individual consumer dynamics, that I see different mechanisms actually happening in this system. And if you look at the papers that are behind it, it's very interesting. This one, what they actually show, what their main message is that the old way of doing these energy forecasts is on all kinds of indicators and complicated modeling. And the way that they made these models, also backcasting with all data to see if they are more, if their models would be better in predicting the development of the past 5 years, if you would have had the data from 5 years ago, 10 years ago, etc. What they do is actually just extrapolating. They call it probabilistic forecasting, but it's just extrapolating. That's what they do. And they show that by simply extrapolating, they do a much better job than all this complicated energy modeling that's behind the old system.
Interesting. Yeah. I think Albert is next.
Wanted to follow up on this, on the politics, and maybe on a global scale, and linking to your ticking clock, and also the other beautiful cartoons in your talk. It made me think of a cartoon that was published in the NRC this week by Fokke and Sukke. I'm sure you've seen it. They're standing there in their boots in Bavaria, right, in the floods, and they're saying to each other, how is this possible, right? We have installed solar panels, and now this happens, right? And so that's the real thing. How can we, on a worldwide scale, solve this problem? I think in China, they're still installing a coal plant every 2 weeks, right? So what can you say a little bit more about your thoughts about how can we think on a global scale, and then things need to be driven by maybe lower costs, because otherwise it's still going to go too slow.
Yeah, so this is a fair point, and indeed China is still deploying a lot of coal, but at the same time they're also deploying a lot of solar and a lot of wind. So I think ultimately it will be indeed a cost competition, especially in those countries. I think we have already benefited so much from the old system that we can afford ourselves to maybe invest a bit more than just only being cost competitive. On a global scale, it's very hard to hold other countries to that same standard, I would say, because I think it's unfair, given the riches that we have had from the gas that we extracted in the Netherlands, to say to other countries that are just starting to develop their economy, you're not allowed to do this anymore. And this kind of dynamics happen in the IPCC, where they have this discussion about how much carbon budget is left for what country. And this is, of course, a very political discussion to have. I think the role that we can play is by being a front runner, showing that you can drive the cost down fast enough, showing that that you can make the system work. You can take like a sort of a moral front runner role, and at the same time build up an industry that will be the future industry, because we just discussed how much needs to be produced, and take a front runner role in that respect that will also benefit your economy.
Yeah. No,
and if we get this between the ears, then we are doing something good.
Right. Yeah. So this is why we need to do research, right? Drive down costs. I think that's super important, so that in the end only rich people can afford fossil fuels.
Yes. Thank you.
Other questions?
Hello, really nice talk. I had a question because I saw the photo of the guy going into the hole, and a few weeks ago I saw a report where they were actually talking about lithium for electric cars, but this is the double side, right? Because this also causes a lot of environmental problems, and this is not fair. So how would you convince these companies that they are really into, we need to get electric cars and we are really focusing on the money, but these people are really having health problems and the environmental causes behind that? That's like really difficult to think about, okay, are electric cars really an option, or how do we do this transition? How do you convince the companies to do it on the right way?
This is a crucial question, but in all fairness, it doesn't only hold for the electric cars. The way that we extract oil or coal or gas, this is the way we treat people. That is the question behind it. How can we convince companies to treat people in the right way? And at the same time that we want to drive costs down on the one hand, to make sure that this doesn't lead to exploitation of workers at the other side of the globe in unworkable conditions. And this is a question that underlies food, energy, and many commodities, our clothes that we wear. I'm not an expert on this whatsoever, but I think it is an important thing to note. It is an important thing that we should act on it. Please bring in the experts that do have expertise on this. I do think it's sometimes used as a false argument to say, okay, we should not go into electric because look at the mines and the cobalt mining, etc., and how poor that is. And for that, I would say we see this in all sectors, and I think we need to acknowledge that we need to act on that. But we need to make sure that it's not used as a false argument to actually hinder the transition at the same time. That will be my answer, yeah.
Yeah, thanks for a very interesting talk. And since we are stepping in a political discussion a bit, I was wondering about, can you comment a bit about the role of fossil source companies in this transition? Because now we have a big share in the business as well, and with PV we are also stepping out, not in an empty space, but yeah, in a place where already occupied by these companies. And yeah, I understand that it can be already a big discussion about it, but maybe you can briefly comment, like, what is the role? Shall we just watch how PV replace their business, or we can cooperate with it? And shall PV community cooperate with them? And yeah, basically this kind of.
Yeah, so this is the thing I've been struggling with the past years. How do you convince industry to actually change course and to focus on what I really believe is going to be also a sustainable business model for them for the years to come? Electrolyzers, building up an electrolyzer manufacturing industry here in the Netherlands, building up a PV manufacturing industry here in the Netherlands, fuel cells. How do you have companies like Shell shift course towards picking up these kind of things? Yeah, it comes down to leadership. I think political leadership to actually provide the pathways to do so, but also within those companies' leadership. And what I see is that the bigger companies, like a Shell, that are very much driven by the interest of the people that have invested in that, and then do not have a strong board that actually counteracts that. Yeah, that this becomes a very complicated mechanic. And what I've actually been observing in the past years is that the startup companies that have more freedom to operate and to act and to build, that they are much better able and much better equipped to actually have this mindset that is societally driven rather than only economics driven, but also as long as it's economics driven, that they can start up something new. And it's much easier to actually let it grow from there than to really change the course of an oil tanker like Shell. And I think ultimately they will win. But what it asks from our government, and that's something that concerns me now, is a willingness to invest in this, also to allow certain companies to fail. If I look at startup nation stuff that's happening in, for example, in Israel, that's a capital of startups, political issues aside at the moment, but the way that they deal with startups is great. I think within Silicon Valley as well, an example. And I think here in the Netherlands, we were taking steps in the right direction. And now we're completely back to square one. So this concerns me because I see a lot of very nice, interesting startups throughout the Netherlands. I know, of course, those in the Eindhoven region very well, but also I see a lot in IPKW, Industriepark Kleefse Waard. There's a number of interesting startups in Groningen. There's a number of interesting startups that really start building up this production capacity. And I think in the Solar NL program you work with Hyatt Solar, that's at the IPKW. I think it's not a startup anymore, but I think these smaller companies, they can grow really fast if we would give the incentives and create boundary conditions to do so. And that requires political will, political stability, and some money to do so. And very sharp changes in policies do not help. So that concerns me, frankly. Yeah.
We have time for one short question. Okay, then I will take my role as chair to ask the last one, which is, you mentioned the scaling. Right now we have economies of scale with really large unit size, and then that helps to make things cheaper, like big chemical plants, big dams, and so forth. And you're proposing a totally different scale where the unit size is small, so the scaling comes in the number of units and not the size of the units. So can you maybe just say a couple words on this? That they're totally opposite and yet somehow both beneficial in scale.
Yeah, this is a very good question. And I've been doing a lot of thinking about this. I'm a chemist from origin, and all the ways that we scaled chemistry and energy in the past were indeed by scaling by size. And some people still try to scale renewables by size. In the old system, it worked really well. Why? Because it was basically a thermally driven process. We are doing a lot of thermochemical stuff in there. We have thermally driven power plants, and there you want to optimize your volume with respect to your surface, because ultimately your surface is a loss. That's where you lose your heat. So you have a 3D scaling law, whereas we are moving in the direction at the moment of electrification of everything, where things happen at the surface, where you have a 2D scaling law instead of a 3D scaling law. So in my mind, this determines also why these mechanics favor, in the new energy system, favor actually a 2D scaling law, and with that scaling up by numbers rather than by size. And also in the production manufacturing, automation of roll-to-roll printing of stuff, etc. It's because we need to maximize the surface rather than minimize the surface. And this change in mindset, I'll be honest, I don't see it in the chemical industry yet. I think also chemistry, you can do small-scale chemistry, electrochemistry with delocalized devices and then bringing it together rather than having one fenced-off chemical plant. I've done some calculations. Do you know how much milk we process in the Netherlands? If you actually look at the amount of, and how decentralized is a cow? A cow is a very decentralized unit, right? Yeah. The amount of milk that we process in the Netherlands is actually more than the amount of diesel and gasoline combined. So we should be able to do it decentralized, I think. But there's a very different mechanism driving this than the 3D scaling law behind the traditional thermochemistry.
Yeah, nice. That's, I think, a wonderful place to end. Let's thank Mark again.